At the heart of a distant galaxy lies Markarian 231, a blazing quasar fueled by one of the hungriest black holes ever found. But how can something that devours everything also shine brighter than billions of suns? Tonight we'll uncover the secrets of this cosmic powerhouse. If you enjoy this journey, please like, subscribe and share, and tell us in the comments, do you think black holes are destroyers or creators of galaxies? Thank you for watching. Now let's begin. Markarian 231 lies in the northern sky within the constellation Ursa Major, far beyond the Milky Way, and yet among the closest quasars ever studied. Its distance, measured in hundreds of millions of light-years, is small, compared with the most remote quasars that shine from the dawn of cosmic time. Because of this relative closeness, its details can be resolved with unusual clarity. This system first appears as a brilliant core set within a faint and irregular halo, a structure that signals both disturbance and intensity. From this vantage point, astronomers place the galaxy within a modest group of companions, a small gathering rather than a dense cluster, but one in which gravitational encounters are strong enough to leave lasting signatures. The galaxy exists as part of the larger cosmic web, a vast arrangement of filaments that stretch across the universe. Along these filaments, matter collects, cools, and forms galaxies, which in turn assemble into groups and clusters. This web-like pattern forms the backdrop to the quasar anchoring it, in a network of associations and interactions. The surrounding environment is neither empty nor passive. Gas flows along filaments, neighbours tug gently over long timescales, and occasional mergers alter the paths of galaxies. It is within this environment that the quasar's host found its identity, shaped not in solitude but through contact with its neighbours. Seen at large scales, the system is distinguished by faint tidal streams. These elongated features are composed of stars and gas pulled outward by gravitational tides during mergers. Such streams stretch for tens of thousands of light-years, delicate threads barely visible against the dark sky. They reveal that the luminous galaxy we see today is the product of at least one major collision. In that encounter, material was torn from the merging partners, creating the arcs and filaments that now extend into intergalactic space. The debris remains as testimony to the forces that drew the galaxies together and bound them into one. This galaxy's neighbours provide a contrast. Many are ordinary spirals or irregular systems, their light dominated by starlight rather than nuclear activity. Against this quieter backdrop, the quasar stands out dramatically, its central brilliance dwarfing the combined output of billions of stars. It is precisely this contrast that makes the object so striking. While companions evolve along calmer paths, this system radiates across the spectrum, its energy fueled by processes at its heart. The surrounding group illustrates that while many galaxies share similar environments, only a few ignite into quasars under the right circumstances. The intergalactic medium within the group contributes to this setting. Though it is almost invisible, this diffuse gas fills the spaces between galaxies. It is heated to high temperatures, producing faint X-ray emission that telescopes can detect. Over time, it receives material expelled from energetic members of the group. The quasar's powerful winds and radiation drive enriched gas outward, altering the medium itself. The exchange is continuous, the environment shapes the galaxy, and in turn the galaxy modifies the environment. This reciprocity is fundamental to galactic evolution, and it plays out clearly here. Deep imaging across wavelengths emphasizes the complexity of the system. Optical telescopes capture the bright core and the faint extended tails. Infrared instruments reveal dust heated by radiation, glowing across the mid and far infrared bands. Radio arrays detect distributions of cold gas stretched out by tidal interactions. Each wavelength uncovers another layer of the system's surroundings, showing how past collisions and current activity combine to shape what we observe. The multi-wavelength approach is crucial because the outer halo, the tidal debris, and the diffuse gas each tell a different part of the story. In this broad neighborhood, the quasar's power becomes even more evident. From a distance of millions of light-years, it appears as a luminous beacon within its group, radiating with far greater intensity than any of its companions. Its brightness is not confined to visible light, but extends across the electromagnetic spectrum, marking it as an object of exceptional energy. Such radiance is uncommon in the local universe. The galaxy's proximity allows detailed examination, making it a rare laboratory for understanding active nuclei and their role in galactic evolution. The system's tidal structures also offer insight into timescales. Stars drawn out during mergers trace paths that persist for hundreds of millions of years before gradually dispersing. Observing them reveals both the violence of the encounter and the slow settling that follows. These faint arcs testify to the long memory of galaxies. Even after central activity dominates attention, the outer reaches preserve evidence of what came before. Thus, the neighborhood does not merely set the stage but continues to bear the marks of past events. Through these perspectives, the galaxy emerges as both a product of its environment and a participant in shaping that environment. Its group supplied companions whose interactions triggered the disturbances now visible. The surrounding medium receives the energy released by its core. The cosmic web holds the group within its vast filaments, guiding flows of matter that eventually found their way into the galaxy's heart. Each scale connects to the next, and in tracing them step by step, one can begin to approach the nucleus, where the greatest energies are released. Markarian 231 is therefore not just a quasar isolated in space, but part of a broader setting, a luminous object born from interactions and still tied to its environment. Its outer neighborhood provides the necessary context to understand why this system shines so intensely, why its halo is disturbed, and why its activity is so pronounced. To move inward requires first acknowledging this cosmic stage, for without it, the inner processes would lack their frame of origin. The galaxy's neighborhood is the beginning of the path toward its core, the first step in exploring the quasar powered by its hungry black hole. Markarian 231 presents itself not only as a point of brightness, but as a galaxy with structure, shape, and scars of past events. Its host is not the smooth rounded form of a quiescent elliptical, nor the calm symmetric spiral seen in undisturbed disks. Instead, it is a disturbed remnant of a merger showing irregular arms asymmetries and signs of violent rearrangement. At galactic scales of tens of thousands of light-years, the system carries evidence of the forces that drove it into its current form. When viewed through deep optical imaging, faint extensions spread outward, resembling ghostly arms pulled from their orbits by tidal interactions. These structures are not decorative, but the real marks of gravity acting over millions of years, pulling and stretching stellar populations into arcs that record the merging history. The body of the galaxy itself is thickened, less defined than a spiral, more clumpy than an elliptical, reflecting the disruption of ordered motion. Astronomers classify it as an ultraluminous infrared galaxy, meaning that the combined light in infrared wavelengths exceeds that of ordinary star-forming systems by orders of magnitude. The source of this extraordinary luminosity lies not only in the nucleus, but also in the massive bursts of star formation triggered across the host. When two galaxies collide, their gas does not remain calm. It is shocked, compressed, and driven into dense regions where new stars ignite at rapid rates. In Markarian 231, these processes have been extreme. Vast regions near the center shine with the glow of young hot stars, their radiation absorbed by surrounding dust and re-emitted in the infrared. The host galaxy therefore glows in that part of the spectrum as strongly as invisible light, and the total output places it among the brightest nearby galaxies known. The structure of the host reveals the consequences of the merger. Its central regions are swollen, not flat like the disk of a spiral, while faint shell-like features and filaments extend outward. The ordered patterns of spiral arms have been replaced by a patchwork of stellar light mixed with dark lanes of dust. Observations show a high concentration of molecular gas in the inner few thousand light-years, indicating that the collision funneled vast amounts of raw material inward. This concentration of gas is unusual compared with quiet galaxies, and is one of the main reasons the system appears so luminous. The reservoir both fuels star formation and supplies matter to the central black hole. The broader halo remains irregular. Surveys detect disrupted companions and faint stellar debris still bound to the system. Some of these fragments may eventually merge completely, while others will disperse into the group environment. Each structure tells of a violent past of galaxies pulled together by gravity, orbiting one another, until friction and tidal forces drove them into coalescence. The result is a host galaxy whose shape is transitional, not yet settled into a new equilibrium. Over billions of years, the system may relax into a more regular elliptical form, but at present it remains caught in the aftermath of its collision. Markarian 231's host is luminous, not only because of its core, but also because of the combination of dust and stars throughout its body. Infrared observations show that the dust is heated to high temperatures, emitting strongly across wide bands. This dust traces both star-forming regions and the shrouding material around the nucleus. In many places, the dust is thick enough to obscure visible light, making the galaxy appear dimmer in optical surveys than its true energy output suggests. Only by observing across multiple wavelengths can astronomers appreciate the full scale of its radiance. The designation as an ultra-luminous infrared galaxy underscores the extraordinary amount of energy irradiated by dust within its structure. The host's disturbed nature also affects the distribution of its stars. Populations of young stars dominate in certain regions, while older populations remain in others, creating contrasts across the galaxy. Young clusters formed from the compressed gas are brilliant but short-lived, destined to fade after only a few million years. Older stars trace the remnants of the original galaxies that merged. The mixture of these populations provides further evidence of the system's violent history, for such juxtapositions rarely occur in undisturbed galaxies. Spectroscopic surveys confirm this variety, showing signatures of both youthful and ancient stellar light. At the scale of tens of thousands of light-years, the shape of the host is far from smooth. It is mottled and asymmetric, lacking the symmetry that characterizes stable spirals. The gravitational torques of the merger have redistributed angular momentum, and the resulting body is more chaotic than orderly. In time, dynamical friction may lead to a smoother distribution, but the current view captures a galaxy in flux. Markarian 231 is therefore not only a quasar, but also a galaxy caught in transformation, its host still bearing the wounds of collision. From the perspective of galaxy evolution, this host is a critical clue. Many models predict that quasars are ignited by mergers, which deliver gas to central regions and fuel black hole accretion. The host of Markarian 231 supports this picture directly. Its irregular form, tidal tails and starburst regions all indicate a merger-driven event. Its classification as both a quasar and an ultraluminous infrared galaxy illustrates the connection between nuclear activity and widespread star formation, both outcomes of the same gravitational disturbance. Observing such a system nearby allows astronomers to connect theoretical models with real evidence. The influence of the host extends beyond its visible features. The mass of stars and gas determines the gravitational potential, guiding how material flows toward the center. In Markarian 231, the deep potential well created by the merged galaxy traps gas, while torques and shocks drive it inward. Without such a massive disturbed host, the central black hole might not be supplied with the matter it requires to shine so brightly. The host is therefore not just a container but an active participant in feeding the nucleus. In summary of its structure, the host galaxy of Markarian 231 stands as a luminous, irregular remnant of a merger, glowing across wavelengths rich in gas and dust, and dominated by both intense star formation and nuclear activity. It is unsettled, asymmetric and bright, a galaxy in transition, whose appearance contrasts sharply with the calmer galaxies nearby. Its form and energy output mark it as extraordinary, providing both the setting and the supply for the quasar at its heart. Step by step, tracing from these galactic scales inward, will reveal how the host connects to the processes that drive the active nucleus. But at this stage, the focus remains on the broader body, the galaxy as a whole, and the scars of its tumultuous history. Markarian 231 shows not only the broad outline of a disturbed galaxy, but also the complex fabric of its interstellar medium, the gas and dust that fill the spaces between its stars. At galactic scales, this medium determines how stars form, how light is absorbed and re-emitted, and how energy moves from one part of the system to another. In a calm spiral galaxy, the interstellar medium is arranged in orderly patterns, along spiral arms with giant molecular clouds, forming stars and diffuse gas filling the gaps. Here the situation is far less regular. The violent merger that shaped the host disrupted the calm distribution of gas and dust, driving vast reservoirs inward and mixing different phases of matter together. The result is a medium that is unusually rich, unusually dense, and unusually turbulent. Radio surveys map the cold molecular gas that serves as raw material for star formation. Observations reveal that Markarian 231 contains billions of solar masses of this gas, an enormous reservoir compared with ordinary galaxies of its size. Instead of lying in thin spiral arms, much of it is concentrated toward the inner regions, but extended components stretch outward as well, remnants of tidal interactions. This cold gas radiates strongly in molecular lines, providing astronomers with a direct measure of its abundance. The richness of this reservoir is one reason for the extraordinary luminosity of the system. Gas not only fuels bursts of star formation, but also supplies the nucleus with material to accrete. In addition to the cold gas, warmer and more diffuse components permeate the galaxy. Ionized gas heated by young stars and by radiation from the nucleus glows in visible emission lines. Filaments of ionized material stretch across thousands of light years, some aligned with outflows driven by the core. Neutral atomic gas contributes as well, mapped through its spectral lines at radio wavelengths. Together these phases form a layered medium complex in both structure and dynamics. Unlike a calm disk galaxy, where phases are distributed in balance, here turbulence and shocks dominate, stirred constantly by the energy released in the central regions, and by the compression induced by the merger. Dust grains, tiny solid particles, are another essential part of the interstellar medium. In Markarian 231, the abundance of dust is immense enough to obscure large portions of the galaxy in visible light. This dust absorbs ultraviolet and visible radiation and re-emits it in the infrared, accounting for the galaxy's extraordinary brightness in that part of the spectrum. Infrared telescopes detect this emission as a broad glow tracing dust both near the center and spread throughout the host. The thick lanes of dust visible in optical images emphasize just how significant this component is. It plays a dual role, concealing the interior from view at some wavelengths, while also revealing the processes at work when examined in the infrared. The turbulence of the interstellar medium is another defining trait. Gas motions in Markarian 231 reach speeds far higher than in calm galaxies, evidence of both the merger's aftermath and the ongoing activity of the nucleus. Shocks travel through the medium, compressing clouds in some places and dispersing them in others. The balance between collapse and disruption determines where stars can form. In regions close to the center, starburst activity shows that compression has won, producing dense clusters of massive young stars. Elsewhere, outflows from the nucleus push gas aside, clearing channels through the medium. The result is a patchwork, a galaxy in which the interstellar material is constantly reshaped by forces from both within and without. Measurements across wavelengths reveal unusual chemical enrichment in this medium. Heavy elements produced by generations of stars are present in high abundance mixed through the gas and dust. These elements, such as carbon, oxygen, and iron, alter how the gas cools and how dust forms. The presence of enriched material indicates long histories of star formation and supernova explosions. In Markarian 231, the merger concentrated this enriched gas in the center, making the medium even more complex. High metallicity, as astronomers call it, affects the efficiency of star formation and the way radiation is absorbed. Thus, the chemistry of the interstellar medium is as important as its dynamics. The distribution of the medium also illustrates the ongoing connection between the host and its environment. Gas pulled in by the merger did not all settle at once. Some remains in extended streams reaching tens of thousands of light years into space. These streams connect the galaxy to its outer halo and to the surrounding group, bridging the scales between galactic and intergalactic. In time, some of this material may fall back in sustaining future star formation. Other portions may be stripped away entirely, adding to the intergalactic medium. Thus, the interstellar matter of Markarian 231 is not confined, but participates in exchanges that link scales from the central core to the cosmic web. Understanding the interstellar medium here is crucial because it provides the immediate context for both starburst activity and nuclear fueling. Without dense molecular gas, new stars would not form at the extraordinary rates observed. Without dust, the infrared luminosity would not be so extreme. Without turbulent flows, gas might not be driven inward to feed the black hole. Every property of the medium contributes to the larger picture of why Markarian 231 is so exceptional. The medium is not passive. It is the fuel, the veil, and the messenger of the galaxy's processes. Astronomers studying this galaxy often emphasize the scale of the gas reservoir compared with typical systems. In ordinary spirals, the amount of cold molecular gas relative to stellar mass is modest. Here the ratio is far higher, a direct consequence of the merger. This gas content explains much of the galaxy's classification as ultraluminous in the infrared. It also signals that the galaxy is in a transient stage. Eventually, as the gas is consumed by star formation or expelled by winds, the luminosity will decline. For now, the medium remains unusually full, and this fullness drives both the visible starburst and the hidden activity of the nucleus. From a broader perspective, the interstellar medium of Markarian 231 illustrates the principle that galaxies are shaped as much by their gas and dust as by their stars. Stars may dominate the light we see, but gas and dust determine the pace of starbirth and the feeding of central black holes. Here those roles are exaggerated to extremes, providing a vivid example of how matter in its diffuse form dictates the evolution of entire systems. At this stage of exploration, attention remains on the galactic scale. The focus is not yet the nucleus itself, but the material that fills the host. The interstellar medium acts as both canvas and fuel, recording the history of past collisions and supplying the energy for current activity. It is turbulent, enriched, and abundant, an environment primed for transformation. To move inward requires passing through this medium, for every step toward the core is shaped by its presence. Markarian 231, seen as a luminous quasar, owes much of its character to the gas and dust spread across tens of thousands of light-years, waiting to be drawn ever closer to the central engine. Markarian 231 contains within its disturbed host regions of extraordinary intensity known as circumnuclear starbursts. These are areas where gas has been compressed to such high densities that stars are born at rates far exceeding those in normal galaxies. At scales of a few thousand light-years around the nucleus, the collision that shaped the galaxy concentrated vast reservoirs of molecular gas. Under the pressure of gravitational collapse and shock compression, this gas formed clusters of massive short-lived stars whose light now fills the surrounding dust with energy. The phenomenon of a circumnuclear starburst is not unusual in merging galaxies, but here it reaches extreme proportions. Observations across infrared wavelengths show that the combined output from these regions alone rivals that of entire ordinary galaxies. The dust absorbs the radiation of young stars and re-radiates it, producing a warm glow that extends over the inner regions of the host. These starburst zones form rings and clumps that encircle the active nucleus. Rather than a smooth disk, they appear as irregular structures where gas is collected unevenly. Radio observations trace concentrations of molecular hydrogen, while optical and infrared views reveal young stellar populations embedded in clouds. Some clusters contain thousands of massive stars, their ultraviolet light hidden from direct sight but detectable through its effects on the dust and gas. Such starburst rings often arise in merger remnants because tidal forces drive gas inward until it stalls at certain radii where it accumulates and collapses. In Markarian 231, the scale of this process is amplified by the enormous amount of gas driven toward the center. The consequences of this starburst activity are profound. Supernova explosions occur frequently in these regions, as massive stars exhaust their fuel in only a few million years. Each explosion releases energy that stirs the surrounding gas, enriches it with heavy elements, and contributes to the turbulence already present. The rate of such events in Markarian 231 is among the highest known, locally adding to the overall luminosity and shaping the dynamics of the circumnuclear medium. Observations of radio emission reveal supernova remnants scattered across the inner regions, markers of how rapidly the stellar population is evolving. The presence of so much star formation near the nucleus creates a complex interplay between stellar processes and black hole activity. On the one hand, the inflow of gas fuels both starbursts and accretion. On the other hand, the energy released by the active nucleus can disrupt star-forming clouds. In Markarian 231, evidence shows that both processes are occurring simultaneously. Regions close to the nucleus are heavily obscured by dust, yet they glow brightly in the infrared, demonstrating that star formation is intense. At the same time, winds from the nucleus push outward carving channels and influencing how gas collapses. The result is a dynamic balance where starburst activity and nuclear outflows coexist and shape one another. Starburst regions also serve as significant contributors to the galaxy's overall infrared output. The heated dust within them radiates strongly, and this emission adds to that of the nucleus itself. For astronomers attempting to measure the power of the central black hole, distinguishing between dust heated by young stars and dust heated by accretion is a challenge. In Markarian 231, both contributions are extreme, and disentangling them requires careful study across multiple wavelengths. This complexity makes the galaxy a key object for understanding how starbursts and quasars overlap, particularly in merger-driven systems. The geometry of these circumnuclear regions further emphasizes the disturbed nature of the host. Rather than forming a neat symmetric ring, the starburst zones are clumpy with bright knots separated by dust lanes. This irregularity is consistent with the chaotic inflows that follow a merger, where gas arrives from different directions and settles unevenly. Within these clumps, stellar densities reach high levels, forming compact star clusters that may eventually evolve into globular clusters. For now, they shine as luminous patches embedded in dusty surroundings. On larger scales, the effects of these starbursts extend outward. Radiation and winds from young stars push on the surrounding medium, adding momentum to gas already being driven by the nucleus. This combined feedback contributes to the galaxy's large-scale outflows, influencing how material is distributed across tens of thousands of light-years. Thus, the circumnuclear starburst is not a separate phenomenon, but part of the broader cycle linking nuclear activity, interstellar medium and galactic evolution. Chemical signatures within these regions highlight their enrichment. Heavy elements produced in massive stars and dispersed by supernovae enrich the gas-raising metallicity levels. This enrichment changes cooling rates and affects how new stars form. In Markarian 231, the abundance of metals in the circumnuclear medium is high, showing that the galaxy has experienced multiple cycles of star formation before and during the current starburst. The dust content is similarly enriched, contributing to the strong infrared emission. These properties confirm that the starburst regions are both energetic and chemically complex. The circumnuclear starbursts of Markarian 231 demonstrate how violent mergers reshape galaxies from the inside out. In a calm galaxy, star formation proceeds at modest rates in extended disks. Here it is concentrated into compact extreme bursts near the center. The energy output from these regions is immense, and the density of activity is far higher than in ordinary systems. This contrast illustrates the importance of environment and interaction in driving galaxy evolution. Without the merger, the gas would not have been funneled inward, and the starburst would not exist at this scale. For astronomers, studying these regions provides critical insight into the connection between star formation and black hole growth. Both processes rely on the same gas, and both release energy that influences the surrounding medium. In Markarian 231, the coexistence of intense starbursts and an active nucleus exemplifies this connection. The circumnuclear starburst is therefore not only a feature of the host, but also a key to understanding the mechanisms that sustain the quasar. As the exploration path moves inward, these regions serve as the immediate environment surrounding the core. They form the interface between the large-scale galaxy and the central engine, bridging tens of thousands of light-years with only a few thousand. The starbursts highlight the continuing transformation of the system, a transformation visible in both light and structure. They demonstrate how the energy of young stars and the gravity of a central black hole together define the character of a galaxy in transition. Markarian 231, through its circumnuclear starbursts, shows how mergers ignite both stellar and nuclear power, making it one of the most luminous galaxies in the local universe. Markarian 231 reveals one of its most dramatic features in the form of kiloparsec-scale outflows, immense winds of gas driven outward across thousands of light-years. These outflows are not gentle breezes, but massive streams of matter accelerated by the energy released in the nucleus and by the combined pressure of intense star formation. When astronomers observe the galaxy at optical and ultraviolet wavelengths, They detect broad absorption lines that signify gas moving at high velocities. In the infrared and radio bands, they trace molecular gas pushed outward on a scale that extends far beyond the circumnuclear regions. The presence of these enormous outflows marks the system as one of the most powerful examples of feedback known in the local universe. The scale of these winds is vast. Gas streams have been measured moving at hundreds to thousands of kilometers per second, carrying away material that would otherwise fuel new stars. Molecular gas, atomic gas, and ionized gas all participate, forming layers of outflow that permeate the host galaxy. Observations show that tens of billions of solar masses of molecular material are involved in a reservoir large enough to alter the future of the system. This expelled matter stretches across kiloparsecs, shaping not only the inner regions, but also the galaxy's extended halo. For astronomers, these outflows provide direct evidence of how energy released near a black hole can influence an entire galaxy. The drivers of such immense winds are multiple. Radiation from the active nucleus exerts pressure on dust and gas, accelerating it outward. At the same time, supernovae from circumnuclear starbursts inject energy into the medium, adding momentum to the flow. Together, these mechanisms produce a multi-phase outflow, with hot ionized gas moving fastest, colder molecular clouds lagging behind, and dust entrained throughout. The combined effect is a broad turbulent stream that escapes the central regions and propagates outward. The scale of the outflow relative to the galaxy's size is extraordinary, for it extends across a significant fraction of the host, reshaping its interstellar medium. The consequences for the system's evolution are profound. By carrying gas outward, the outflow depletes the reservoir needed for star formation. If the process continues, it can quench future starburst activity, leaving the galaxy with fewer raw materials to form new stars. This mechanism, often called feedback, is thought to explain why some galaxies stop forming stars and evolve into more passive systems. In this case, the feedback is visible in real time, offering astronomers a chance to study directly how black holes regulate growth. The impact is not confined to the inner kiloparsec, but stretches across the galaxy, linking the nucleus to the larger structure. Detailed mapping shows that the geometry of the outflow is not uniform. Conical structures extend from the center, aligned with openings in the surrounding dust. These cones are filled with ionized gas glowing in emission lines, while molecular gas is seen flowing along their edges. Such geometry suggests that the outflow is shaped by the structure of the circumnuclear medium, which channels the flow into particular directions. The alignment of these cones provides clues about the orientation of the inner region's information otherwise hidden by dust. The shapes are evidence that the connection between the nucleus and the host is not random but structured, with outflows carving distinct paths through the galaxy. Measurements of velocity and mass outflow rate highlight the extreme nature of the phenomenon. The system expels several hundred solar masses of gas each year, far more than the star formation rate in many galaxies. Over time, this rate is enough to strip the inner regions of their gas content. Such depletion alters the balance between starburst activity and nuclear fueling. By pushing away the very matter that sustains it, the nucleus may regulate its own growth, preventing the black hole from accreting indefinitely. This self-regulating cycle is a cornerstone of models of galaxy evolution, and here it is observed in remarkable detail. The influence of the outflow extends beyond the host itself. As gas is expelled into the surrounding halo, it enriches the intergalactic medium with heavy elements. Metals produced in stars and dispersed by supernovae are carried outward, mixing with the tenuous gas between galaxies. Over cosmic timescales, this process seeds the environment with the ingredients necessary for future generations of galaxies. Thus, the outflow is not only destructive, but also creative, distributing material that may eventually contribute to star formation elsewhere. The galaxy becomes both a consumer and a donor, taking in gas through mergers and releasing enriched matter through winds. From a chemical perspective, the outflows are particularly important. They carry dust as well as gas, and this dust absorbs radiation, altering how light escapes from the galaxy. In the infrared, the heated dust glows, while in optical wavelengths, the dust dims the view. The combination of absorption and re-emission shapes the observed spectrum across the electromagnetic bands. For astronomers attempting to separate nuclear and stellar contributions, the presence of dust-laden winds complicates the picture, yet it also provides valuable data on the interaction between radiation and matter on galactic scales. Observations in X-rays further reveal the role of hot gas in these outflows. High-energy emission marks regions where shocks heat material to millions of degrees Celsius. These hot phases move rapidly and expand into the halo, carrying energy as well as mass. The multi-phase nature of the outflow from cold molecular clouds to hot plasma illustrates the complexity of feedback in action. Each component responds differently to forces, yet together they create a single coherent phenomenon. This unity across phases makes the system a benchmark for studies of feedback. The visual impression of these outflows when reconstructed from data is that of a galaxy surrounded by faint extended plumes. They are not immediately obvious to the eye, but become clear when emission lines and absorption features are mapped. These plumes extend for thousands of light years, faint but significant, forming a halo of expelled material. Within them lie streams of gas moving at hundreds of kilometers per second, mixed with dust and enriched elements. Their existence confirms that the energy of a black hole can influence not just its immediate surroundings, but entire galaxies. For galaxy evolution, the lesson from these outflows is clear. Without them, gas would continue to accumulate in the center, driving unending starbursts and uncontrolled black hole growth. With them, the system is forced into balance, its growth limited by its own energy release. Markarian 231 demonstrates this balance vividly, showing how feedback transforms a galaxy in the midst of its active phase. For astronomers, the study of such outflows provides both a local example and a template for understanding distant quasars, where similar processes occur on even grander scales. As the path of exploration moves inward, these kiloparsec-scale winds represent the outermost influence of the nucleus. They connect the small scales of accretion to the large scales of the host, bridging the gap between black hole physics and galaxy-wide transformation. They are the fingerprints of interaction between central engines and their galaxies, visible in motion, structure, and chemical makeup. This system, by exhibiting such strong and extended outflows, underscores the fundamental role of feedback in cosmic history. The next step is to follow the flow of matter inward toward the obscuring material that hides the nucleus from direct view, and to examine how the inner structure gives rise to such power. Markarian 231 draws attention inward from the vast outflows toward the dense and obscuring layers of gas and dust that surround its active nucleus. These inner regions, often described as circumnuclear obscuration, form the barrier that hides the black hole and its immediate environment from direct optical view. Instead of an open line of sight, astronomers detect heavy absorption, scattering and re-radiation, all signs that matter is gathered in thick clouds close to the center. This obscuring structure is not uniform but clumpy, irregular, and dynamic, constantly shaped by inflows from the galaxy and outflows from the nucleus. Observations across infrared and submillimeter wavelengths reveal the presence of enormous quantities of warm dust concentrated within a few hundred parsecs, heated both by young stars and by the radiation of the accreting black hole. It is through this shroud that much of the galaxy's radiant energy escapes, absorbed at short wavelengths and re-emitted at longer ones. The geometry of this obscuring material is critical. Rather than a thin veil, the region is thick and extended, forming a torus-like distribution that blocks certain lines of sight while leaving others more open. Depending on the orientation, an observer may see either a bright quasar or a heavily obscured nucleus. In the case of this system, dust lanes and clouds block much of the direct radiation, making infrared and X-ray observations essential to probe inside. This torus is not a smooth ring, but an assembly of countless clouds orbiting under the influence of gravity and stirred by turbulence. Between the clouds are gaps through which some radiation escapes, while other paths remain fully blocked. The result is a complex interplay of transparency and opacity that determines how the nucleus is viewed. Infrared surveys show that the dust within this obscuring zone reaches temperatures of hundreds of degrees Celsius, glowing brightly across wide bands. This emission is one of the defining features of ultraluminous infrared galaxies. In Markarian 231, the intensity of this thermal radiation indicates that enormous amounts of energy are being absorbed and reprocessed. The obscuring material therefore acts not only as a shield, but also as a converter, taking high-energy light from the nucleus and young stars and re-radiating it into longer wavelengths that escape more easily. Astronomers studying the spectral energy distribution of the galaxy find that much of its output comes from this process, evidence that the shroud plays a central role in shaping the observed properties. The dynamics of the obscuring region are equally important. Gas and dust are not static but move under competing influences. Gravitational attraction draws material inward, supplying fuel to the black hole. Radiation pressure pushes outward, attempting to clear paths. Magnetic fields thread through the clouds, adding further complexity to their motion. As a result, the torus is a turbulent environment, constantly shifting and changing. Observations suggest that the covering factor, the fraction of the nucleus hidden at any given time, can vary as clouds move along their orbits. Such variability affects how the galaxy is classified and how its energy is distributed across wavelengths. Chemical composition within the obscuring region also provides key clues. Dust grains contain silicates and carbon compounds, producing distinctive absorption features in infrared spectra. Gas within the region is enriched with heavy elements from past star formation. These chemical fingerprints confirm that the material originates from the galaxy itself, funneled inward from larger scales and concentrated around the nucleus. In Markarian 231, the abundance of dust and metals is particularly high, reflecting its violent history and rich star-forming environment. This enrichment affects how radiation is absorbed and re-emitted, making the obscuration both dense and efficient. The obscuring material also defines the boundary between the starburst regions and the active nucleus. Just beyond the torus, circumnuclear star formation, occurs its light heavily absorbed by dust. Within the torus, matter spirals closer to the black hole where conditions change rapidly. The interface between these zones is a region of intense complexity, where inflowing gas meets outflowing winds, and where new stars may form even as radiation tears clouds apart. This interface is crucial for understanding how galaxies regulate the delivery of material to their central engines. Astronomers use multiple wavelengths to probe this obscured nucleus. In X-rays, high-energy photons penetrate some of the dust, though they are partially absorbed, producing spectra that reveal the density of intervening material. In the mid-infrared, emission from heated dust dominates, mapping the temperature and distribution of the torus. In radio waves, mass emission from molecules traces motions deep inside, providing direct evidence of rotation and inflow. Together, these observations construct a picture of a nucleus heavily wrapped in matter, yet still radiating immense energy through reprocessed light. The presence of this obscuration has broader implications. It demonstrates that the central black hole cannot be understood without considering its environment. The obscuring torus both hides and reveals both blocks and channels energy. Its thickness explains why quasars can appear so different depending on orientation. In the case of this system, the heavy shrouding confirms that the nucleus is in a deeply embedded phase, still cocooned in the gas and dust delivered by the merger. Over time, feedback may disperse much of this material, unveiling a more classical quasar. For now, the obscuration remains a defining trait shaping every observation. From the perspective of galaxy evolution, the obscuring region is an essential part of the feedback cycle. Gas is driven inward by tidal forces and compression forming the torus. The nucleus then releases radiation that heats and pushes on this same gas, driving outflows that limit further inflow. The balance between these processes determines how long the nucleus shines at peak luminosity. In Markarian 231, the heavy obscuration signals that the system is still in a phase of intense growth, with the black hole accreting vigorously while buried in material. The torus records this stage, its properties reflecting both the feeding of the black hole and the resistance of the surrounding gas. Visualizing the obscuring region emphasizes its scale. Though only a few hundred parsecs across it plays a role that influences the entire galaxy. Light from the accretion disk cannot escape directly along most lines of sight. Instead, it heats the dust which radiates outward in infrared waves detectable across cosmic distances. This re-radiated glow dominates the galaxy's energy budget, making it one of the brightest infrared sources in the nearby universe. Without the obscuring torus, the quasar would appear entirely different, its power measured in other wavelengths. The shroud transforms both the appearance and the impact of the nucleus. The inward journey toward the black hole must pass through this dense region. It is here that matter accumulates, here that energy is converted, and here that the visible character of the galaxy is determined. The obscuration is not a mere byproduct, but a central element of the system binding together the processes of star formation, accretion, and feedback. By studying it, astronomers glimpse both the immediate conditions near the black hole and the broader cycle that links nuclear activity to galaxy-wide transformation. This stage marks the transition from galactic scales to nuclear scales, from thousands of light-years to hundreds, and from the visible universe to the hidden heart of one of the nearest and most luminous quasars. Markarian 231 continues to guide the path inward to the structure known as the dusty torus, the donut-shaped distribution of gas and dust that envelops the active nucleus. This torus is one of the defining components of active galactic nuclei across the universe, but in this system it is especially pronounced, glowing brightly in the infrared as it absorbs the intense radiation from the black hole and from surrounding starbursts. The torus is not smooth or uniform. Instead, it consists of countless dense clouds orbiting at distances of tens to hundreds of parsecs from the center. These clouds are heated to high temperatures ranging from a few hundred to more than 1,000 degrees Celsius, and they radiate strongly, producing the thermal emission that dominates the mid-infrared spectrum of the galaxy. The torus acts as both a veil and a lens. It hides the inner regions from direct view in visible light, while re-emitting their energy in longer wavelengths that escape more easily. The geometry of this structure is key to understanding the varied appearances of quasars. Depending on the viewing angle, an observer may see directly into the nucleus, or may instead see a heavily obscured system dominated by infrared emission. In the case of this galaxy, the orientation places thick dust clouds across most direct sightlines, meaning that the nucleus is hidden and its presence is revealed only through absorbed and scattered radiation. This obscuring geometry is one reason the galaxy is so luminous in the infrared. The torus converts the short wavelength output of the accretion disk and corona into longer wavelength light, allowing the system to shine with extraordinary brightness even when the core itself is invisible. The torus also serves as a critical interface between the feeding of the black hole and the feedback it produces. Gas driven inward from larger scales collects in this region, orbiting in thickened distributions before spiraling further down. At the same time, radiation from the nucleus pushes outward on the clouds, heating them, dispersing some, and sculpting gaps through which light can escape. The balance of these forces defines the thickness and covering factor of the torus. In Markarian 231, the torus is exceptionally thick, suggesting that inflows from the merger continue to deliver material faster than outflows can clear it. This places the system in an embedded growth-dominated phase, where accretion proceeds at high rates while still wrapped in gas and dust. Astronomers probing the torus rely on infrared interferometry and sub-millimeter observations to resolve its structure. These data reveal clumpy distributions rather than smooth rings consistent with theoretical models that predict turbulence and fragmentation. The clumps move in orbital paths set by the central gravity colliding and dispersing as they orbit. Between the clumps are open channels through which radiation escapes, producing variability in observed spectra. These observations suggest that the torus is not a static structure, but a dynamic, evolving environment where clouds form, move, and dissipate on timescales of thousands to tens of thousands of years. The dust composition within the torus reveals further complexity. Infrared spectra show silicate features both in emission and absorption, indicating that the clouds are rich in silicate grains mixed with carbonaceous material. These grains determine how radiation is absorbed and scattered. The silicate absorption features in particular confirm that thick columns of dust lie along our line of sight. In Markarian 231, these features are among the strongest measured in nearby quasars, highlighting the exceptional column densities involved. Such dust not only obscures, but also contributes to the reprocessed glow that dominates the system's energy budget. The torus also provides the stage for molecular mesa emission. Observations in radio wavelengths detect water masses within the obscuring clouds, amplified by the extreme conditions of density and temperature. These matters trace the rotation of the torus, offering direct measurements of its kinematics. From such data, astronomers infer that the torus rotates at hundreds of kilometers per second, orbiting under the gravitational pull of the central black hole. These measurements provide some of the most direct evidence of the massive object hidden within, linking the obscuring structure to the unseen engine it surrounds. From a theoretical perspective, the torus is an essential part of unification models of active galactic nuclei. These models propose that quasars and other active galaxies can appear different, not because of intrinsic distinctions, but because of orientation relative to the torus. If the nucleus is visible, the system appears as a bright, unobscured quasar. If the nucleus is hidden, the system appears as an obscured quasar or as an ultraluminous infrared galaxy. Markarian 231 exemplifies the latter case, heavily buried within dust, shining most strongly at longer wavelengths. Its torus demonstrates how geometry and orientation shape observation, emphasizing the importance of structure at these scales. The influence of the torus on galaxy evolution is significant. By holding large amounts of gas and dust, It regulates how much material reaches the accretion disk and how much is blown outward. It acts as both a reservoir and a filter. Inflows from the galaxy supply the torus, and from it gas either continues inward to feed the black hole or is driven away in outflows. In this way, the torus mediates the growth of the nucleus and the impact of feedback. The thickness of the torus in this galaxy suggests that the feeding process remains vigorous, while the winds escaping through its gaps show that feedback is simultaneously active. For astronomers, studying this structure provides one of the best opportunities to connect large-scale galactic phenomena with the physics of black hole accretion. The torus is large enough to be resolved in nearby systems, yet close enough to the nucleus to reflect its influence directly. In Markarian 231, the torus bridges scales of hundreds of parsecs, with processes occurring near the event horizon, offering a rare link between galactic and relativistic regimes. Its properties, thickness, clumpiness, temperature composition, encode the history of inflow and the dynamics of feedback, making it a key focus of ongoing study. Visually, the torus would appear as a dense darkened band surrounding the hidden nucleus, glowing invisibly in the infrared while blocking most optical light. To the human eye it would be opaque, but to telescopes tuned to the right wavelengths, it is brilliant, radiating the energy of both stars and accretion. It is a paradoxical structure, both concealing and revealing, both feeding and limiting. Without it, the character of the quasar would be entirely different. With it, the system appears as one of the most luminous infrared sources in the nearby universe. The inward exploration has now reached the scale of the torus, a region where galactic matter condenses into the environment that hides and shapes the active nucleus. This stage marks the transition from the broad scales of starbursts and outflows to the more compact processes that feed the black hole itself. The torus is the gateway to the inner regions where radiation pressure, magnetic fields, and extreme gravity define the next steps of the journey. Markarian 231, when studied more closely, reveals another of its defining characteristics: the presence of broad absorption line winds that sweep outward from the nuclear regions and carry signatures of gas accelerated to extreme velocities. These winds are detected through their imprints on the light from the nucleus, where deep, wide absorption troughs appear in the spectra at ultraviolet and optical wavelengths. Such features indicate that gas along the line of sight is moving at thousands of kilometers per second, fast enough to escape the gravitational pull of the galaxy itself. The winds are not confined to a narrow region, but extend across wide angles, forming a broad outflow that removes matter from the immediate surroundings of the black hole. In this system, the absorption lines are among the strongest seen in any nearby quasar, confirming that the winds are both powerful and pervasive. The physical origin of these broad absorption line winds lies in radiation pressure, as the accretion disk around the black hole shines with intense ultraviolet light. Photons collide with atoms in the surrounding gas, imparting momentum and pushing them outward. This process, known as line driving, is particularly effective when atoms absorb photons at specific wavelengths. In the dense environment of the torus and inner accretion, flow radiation pressure accelerates clouds of gas to tremendous speeds, creating the observed absorption features. In addition to line driving, thermal winds and magnetic processes may contribute, but in this galaxy, radiation pressure is believed to be the dominant force. The result is a continuous stream of matter, leaving the inner regions stripping gas away before it can fall all the way into the black hole. Observationally, the winds are complex. Spectra reveal multiple absorption troughs, each corresponding to gas at different velocities. Some components move at only a few thousand kilometers per second, while others reach up to 30,000 kilometers per second. The depth and breadth of these lines confirm that a significant fraction of the nucleus is covered by outflowing gas. In some cases, the absorption features vary over time, suggesting that clouds pass through the line of sight, or that the strength of the wind itself fluctuates. These variations demonstrate that the winds are clumpy rather than uniform, composed of countless discrete structures embedded in a broader flow. The impact of such winds on the surrounding galaxy is profound. By carrying away large amounts of gas, they regulate how much matter remains available for both accretion and star formation. Estimates suggest that the winds in this system remove several solar masses of material each year, an amount comparable to or greater than the rate of accretion onto the black hole. Over cosmic timescales, such losses are enough to starve the nucleus and to alter the course of the host galaxy's evolution. The winds thus act as a self-limiting mechanism, ensuring that the black hole cannot grow without bound. Broad absorption line winds also provide clues to the structure of the nuclear regions. Their presence requires that radiation from the accretion disk be at least partially visible to the outflowing gas. This implies that the winds arise from intermediate zones between the disk and the torus where radiation can escape, but matter is still dense enough to be accelerated. Models suggest that the winds originate at radii of a few hundred to a few thousand times, the distance between Earth and the Sun placing them well within the gravitational sphere of the black hole, yet far enough that radiation pressure can dominate. In this system, the strength of the winds indicates that these zones are unusually rich in gas, consistent with the galaxy's overall abundance of material delivered by its merger. The winds are also significant for their role in shaping the observed spectra of quasars. In systems without such winds, the light from the accretion disk is seen relatively unaltered. In systems with broad absorption lines, the spectra are deeply carved with large portions of the ultraviolet continuum absorbed. Markarian 231 belongs to this latter class, providing one of the nearest laboratories for studying the phenomenon. Its spectra show strong absorption in lines of carbon, silicon and magnesium, among others confirming both the velocity and the chemical composition of the winds. The chemical enrichment reflects the history of star formation in the galaxy, showing that the outflowing gas carries elements forged in previous generations of stars. Another important aspect of the winds is their geometry. They are not confined to a single narrow jet, but instead spread across a wide angle, covering much of the sky as seen from the nucleus. This wide-angle nature means that they can influence a significant fraction of the host galaxy. Unlike collimated jets that affect only narrow channels, broad absorption line winds sweep across large regions, distributing energy and momentum widely. This geometry explains why their impact on star formation and gas distribution is so extensive. The connection between the winds and variability in the galaxy's brightness has also been noted. Changes in absorption features sometimes coincide with changes in the luminosity of the nucleus, suggesting a close link between the accretion rate and the strength of the outflows. When the black hole accretes more vigorously, radiation pressure strengthens and the winds intensify. When the accretion slows, the winds weaken. This feedback loop ties the inner accretion processes directly to the large-scale properties of the galaxy, further emphasizing the interconnectedness of scales. From a theoretical standpoint, broad absorption line winds are crucial for understanding the coevolution of black holes and galaxies. They provide one of the clearest mechanisms by which energy and matter are transferred from the small scales of accretion disks to the large scales of host galaxies. In the case of this luminous system, the winds are strong enough to drive changes across thousands of light years, demonstrating that even processes occurring near the event horizon can shape entire galactic structures. For astronomers, the proximity of this galaxy offers a chance to study these processes in detail, connecting observations to models of distant quasars. Visually, if one could somehow see these winds, they would appear as vast, invisible rivers of gas flowing outward from the nucleus, sweeping across wide cones and carrying with them dust and enriched elements. They would not form sharp boundaries, but would instead appear as shifting, translucent veils, dense in some regions, diffuse in others, constantly in motion. Against the bright background of the accretion disk, they would reveal themselves through their shadows, absorbing light at specific wavelengths and leaving imprints on the spectrum. Their presence would be undeniable, even if their form remained hidden. The journey inward has now passed through the outflows on kiloparsec scales and arrived at the winds much closer to the nucleus. These broad absorption line features mark a stage where radiation interacts directly with matter, where photons accelerate gas into high-speed flows that both feed back on the galaxy and regulate the black hole's growth. They are the signature of a system in balance, one that consumes gas while simultaneously expelling it, one that shines with extraordinary power while hiding much of its inner life behind layers of dust and winds. This stage sets the foundation for the next step inward toward the accretion flows at larger radii, where gas transitions from galactic inflow to the direct grasp of the black hole's gravity. Markarian 231 draws the focus still closer to its core, where the inflow of matter begins to form the structures that supply the black hole. This stage is described as the outer accretion flow, the region where gas that has travelled inward from kiloparsec scales gathers, cools, and starts to settle into organised motion. At these radii hundreds to thousands of times the distance between Earth and the Sun, the gas has not yet formed the compact accretion disk, but is already under the strong gravitational pull of the nucleus. The flow here is chaotic yet directional, with material spiralling inward, while shedding angular momentum through turbulence and magnetic interactions. In this system, the reservoir of inflowing gas is unusually large because of the merger that delivered vast amounts of material to the centre. Observations confirm dense concentrations of molecular gas extending into the inner few hundred parsecs, and from this reservoir the outer accretion flow takes shape. The gas at these distances is multiphase, meaning it exists in different forms at once. Cold molecular clouds, warm atomic gas, and hot ionized plasma all share the region, moving at different speeds and colliding in turbulent flows. The coldest material is detected in carbon monoxide lines at millimeter wavelengths, indicating massive clouds that retain their molecular form despite the surrounding heat. Warmer atomic gas emits spectral lines at optical wavelengths, while hot plasma radiates in X-rays. Together, these phases paint a picture of a medium that is both clumpy and dynamic, shifting constantly as inflow competes with outflow. In Markarian 231, the dominance of molecular gas is a distinctive feature reflecting the merger-driven abundance of fuel. The motions within the outer accretion flow are not uniform. Some material moves in relatively coherent spirals, while other portions plunge inward in chaotic paths. Observations of maser emission trace rotation in the inner molecular disk, but beyond this turbulence dominates. Shocks form where gas clouds collide, heating portions of the medium and causing local instabilities. These shocks dissipate energy and help transfer angular momentum outward, a requirement for accretion to proceed. Without such mechanisms, gas would orbit indefinitely. Instead, collisions and turbulence allow material to lose energy and spiral closer to the black hole. This process is not smooth, but occurs in bursts with clumps of gas moving inward episodically. Dust remains abundant in this outer flow, obscuring direct views and altering how radiation escapes. The dust absorbs ultraviolet and visible light from the nucleus and re-emits it in infrared, blending the output of the central engine with the glow of the surrounding material. Infrared interferometry reveals extended emission consistent with warm dust distributed over hundreds of parsecs, confirming the scale of the outer flow. In Markarian 231, this dust is particularly thick, a continuation of the dense environment already observed in the Taurus and Starburst regions. It both hides the inflow and testifies to its richness. The role of magnetic fields in this region is subtle but important. As gas moves inward, tangled magnetic lines thread through the medium coupling motions of charged particles and creating stresses that redistribute angular momentum. This magnetic turbulence enhances the efficiency of accretion, converting orbital energy into heat and radiation. Although difficult to observe directly, indirect evidence from polarization measurements suggests that magnetic activity is strong in the central regions of the galaxy. In the outer flow, magnetic effects combine with shocks to sustain the inward motion of gas. Chemical enrichment continues to mark the material here. The gas carries heavy elements produced in earlier generations of stars mixed with dust grains that survived the journey inward. These metals alter cooling rates, allowing gas to lose energy efficiently and collapse further. Enriched gas also supports molecule formation, explaining the high abundance of molecular species observed in this system. The chemistry of the outer accretion flow therefore reflects both the history of star formation in the galaxy and the current processes delivering matter to the black hole. The balance between inflow and feedback is delicate. While gas moves inward to feed the nucleus, radiation pressure and winds from closer in push outward. The outer accretion flow is where these forces meet. Some clouds succeed in moving closer while others are halted or even expelled. This constant interplay creates a dynamic equilibrium with inflow continuing, but at a rate regulated by the very energy it helps produce. In Markarian 231, the large supply of gas ensures that inflow remains significant, despite the resistance sustaining one of the most luminous quasars in the nearby universe. The variability of the nucleus is partly tied to this outer flow. As clumps of gas move inward, they can temporarily increase the accretion rate, leading to changes in luminosity. Conversely, when outflows sweep away portions of the flow, the accretion rate may decrease. These variations occur over timescales of years to decades, observable in long-term monitoring. The link between the outer flow and nuclear variability is one of the ways astronomers connect galactic-scale processes with the behavior of the black hole. Theoretical models of galaxy evolution emphasize the importance of such outer accretion flows. They provide the bridge between the interstellar medium on kiloparsec scales and the relativistic accretion disk on subparsec scales. In Markarian 231, this bridge is unusually massive, reflecting the exceptional supply of gas delivered by the merger. Studying it provides rare insight into how black holes are fueled during their most active phases. Observations across millimeter infrared and X-ray wavelengths all converge on the picture of a dense, turbulent and enriched flow that delivers material steadily inward. Visually, this outer flow would not appear as a neat disk, but as a stormy and chaotic region filled with clumps of gas and dust glowing faintly in infrared light, while hiding its true complexity behind veils of obscuration. Against the brightness of the nucleus, it would be invisible to the human eye, yet its presence is revealed through spectral lines and radiation signatures. It is the hidden highway along which matter travels the zone where galactic material transitions into the direct grasp of the black hole's gravity. Markarian 231 in this stage of inward exploration shows how the outer accretion flow serves as the gateway to the nucleus. It gathers the gas delivered by galactic processes, organizes it into spiraling paths, and regulates how much reaches the inner disk. It is both chaotic and ordered, turbulent yet directional, enriched yet still evolving. By understanding this stage, astronomers connect the vast scales of mergers and starbursts to the intimate scales of black hole accretion. The outer flow is the meeting ground of galaxy and nucleus, and in this luminous system it operates at a scale and richness unmatched in most nearby quasars. Markarian 231, viewed still further inward, reveals the formation of the inner accretion disk, the flattened structure of gas spiraling at tremendous speeds close to the black hole. This disk is the direct engine of the quasar, where gravitational energy is converted into radiation with extraordinary efficiency. Gas that has travelled through the chaotic outer flow now settles into a more organised form, compressed into a disk only light years across, yet capable of outshining the combined starlight of the entire galaxy. The conditions here are extreme temperatures reach tens of thousands to millions of degrees. Celsius densities are immense, and orbital velocities approach a significant fraction of the speed of light. The radiation produced emerges across the electromagnetic spectrum from optical light to ultraviolet and X-rays, giving the quasar its distinctive brilliance. The physics of the accretion disk begins with gravity. As gas spirals inward, it loses gravitational potential energy, which is transformed into heat through friction and turbulence within the disk. This heat causes the disk to glow brightly. The innermost regions radiate at the highest temperatures, emitting ultraviolet and soft X-rays, while the outer portions shine in optical and infrared light. The gradient in temperature creates a spectrum that spans multiple wavelengths, one of the hallmarks of quasars. In Markarian 231, this emission is partially hidden by dust, but observations that penetrate the obscuration reveal the unmistakable signs of a hot luminous disk. The structure of the disk is not static. Magnetic turbulence generated by the magnetorotational instability stirs the gas and allows angular momentum to be transported outward. Without this mechanism, gas would be trapped in stable orbits and accretion would stall. Instead, magnetic interactions between orbiting particles enable them to trade momentum, allowing some material to move outward, while the rest sinks deeper into the gravitational well. This process sustains a continuous flow, driving gas toward the event horizon while releasing enormous amounts of energy. Theoretical models predict that up to 10% of the rest mass of accreted material can be converted into radiation of far higher efficiency than nuclear fusion in stars. This explains why the disk around the black hole dominates the luminosity of the galaxy. The geometry of the inner disk is thin compared with its radius, a pancake-like structure only fractions of a light-year in height, yet many light-years wide. In Markarian 231, evidence suggests that radiation pressure thickens the disk in the innermost regions, producing a puffed-up structure that further enhances outflows. The balance between gas pressure, radiation pressure, and gravity determines the shape of the disk. In high luminosity systems such as this, one radiation pressure dominates, making the disk unstable in places and prone to fluctuations. These instabilities may explain the variability observed in the galaxy's light, as portions of the disk brighten or dim depending on changes in accretion rate and structure. The disk's emission is not uniform. Different radii contribute differently to the total light. The outer zones radiate mostly in optical wavelengths, producing a thermal continuum similar to that of a star but far brighter. Moving inward, the temperature rises and ultraviolet light dominates. Closest to the black hole, the temperatures are so high that soft X-rays emerge. Observing this multi-wavelength emission allows astronomers to map the disk indirectly, inferring its structure from its spectrum. In Markarian 231, this mapping is complicated by heavy obscuration, but X-ray and infrared data confirm the presence of a hot luminous disk hidden behind veils of dust. The dynamics of the disk are revealed through spectral lines broadened by Doppler shifts. Gas orbiting at thousands of kilometers per second produces wide emission lines with distinctive profiles. These lines provide evidence of the disk's rotation and help measure the velocity and distribution of the material. In this galaxy, broad emission lines in hydrogen and other elements confirm the existence of a dense, fast-moving disk close to the black hole. The profiles of these lines also suggest turbulence and warping features consistent with the disk under the influence of both gravity and radiation pressure. Another key feature of the disk is its interaction with the corona, the halo of extremely hot electrons that surrounds it. Radiation from the disk is scattered by these electrons, producing X-rays through a process called inverse Compton scattering. The relationship between disk and corona explains the multi-wavelength variability observed in the quasar. In Markarian 231, unusual X-ray spectra suggest that the corona may be unusually compact or obscured, making the system distinct from many other quasars. This peculiarity has made the galaxy an object of special interest, as it challenges simple models of disk and corona structure. The disk is also the source of strong winds that contribute to the outflows already observed on larger scales. Radiation pressure near the inner edge accelerates gas upward from the disk's surface, creating line-driven winds that escape along wide angles. These winds are seen in absorption features that vary with time, further evidence of the disk's dynamic nature. In this system, the combination of disk winds and broad absorption line outflows illustrates the multiple pathways by which energy and matter leave the nucleus, connecting small scales to galactic scales. From a theoretical perspective, the accretion disk is central to understanding quasar activity. It is the structure that converts the gravitational energy of infalling gas into radiation, powering the galaxy's extraordinary luminosity. In the case of Markarian 231, the disk is fed by an abundant supply of gas delivered by the merger and sustained by turbulence in the outer flow. Its efficiency ensures that even small amounts of mass can produce vast amounts of light. By studying its emission, astronomers test models of accretion physics and refine estimates of black hole mass and growth rate. Visually, if one could see through the obscuring dust, the disk would appear as a brilliant, flattened whirlpool of light, its inner regions glowing white-blue from ultraviolet emission, its outer regions shaded toward red and orange. The brightness would be overwhelming, outshining the stars of the host galaxy by orders of magnitude. To the human eye, it would seem like a blazing ring suspended in darkness, spinning rapidly around an unseen center. The heat and motion would be beyond direct perception, but the light would testify to the extreme conditions within. In the context of the inward journey, the inner accretion disk represents the transition from galactic processes to relativistic ones. It is the place where matter ceases to behave like clouds and streams, and instead forms a compact rotating engine under the black hole's grip. It is both the culmination of inflow and the origin of outflow, the point where gas finally surrenders its energy and radiates it outward. For Markarian 231, the disk explains the quasar's brilliance, its variability, and its influence on the galaxy as a whole. The next step will lead even closer to the corona, and to the interplay of magnetic fields and radiation that dominate the regions just above the disk's surface. Markarian 231, when examined still further inward, brings attention to the hot corona, a region of tenuous yet extremely energetic plasma hovering above and below the accretion disk. Unlike the relatively cooler disk that emits thermal radiation, The corona is a cloud of electrons heated to temperatures reaching hundreds of millions of degrees Celsius. These electrons interact with photons emerging from the disk, scattering them to higher energies in a process known as inverse Compton scattering. As a result, soft ultraviolet and optical photons from the disk are boosted into X-rays, creating one of the defining signatures of an active galactic nucleus. In this system, the corona's presence is inferred not only from its X-ray spectrum, but also from the unusual variability in absorption patterns observed when the galaxy is monitored over time. The precise geometry of the corona is uncertain, but evidence suggests it may form a compact region near the black hole or an extended layer above the disk. In Markarian 231, X-ray observations reveal that the corona may be weaker or more compact than in typical quasars, a peculiarity that has drawn significant attention. Some studies suggest that much of the X-ray emission is heavily absorbed by surrounding gas, while others indicate that the corona itself may be unusually small. Regardless of its geometry, the corona plays a central role in the energy balance of the system, transforming a fraction of the disk's radiation into high-energy light that escapes the galaxy. The process of inverse Compton scattering within the corona illustrates the interplay between matter and radiation under extreme conditions. Photons striking electrons at such high temperatures gain energy-producing spectra that extend into hard X-rays. The slope and intensity of these spectra provide direct clues to the temperature and density of the corona. In this galaxy, the observed spectra are unusually flat, suggesting a hot but perhaps optically thick corona. This complexity makes the system an important case study, as it challenges simple models that assume uniform extended coronas. The corona is also linked to variability in the quasar's output. Changes in the structure or temperature of the electron cloud can cause fluctuations in the X-ray emission on timescales of hours to days. Monitoring reveals that the galaxy shows unusual variability patterns, sometimes dimming unexpectedly in X-rays while remaining bright in the infrared. Such behavior suggests that obscuring clouds may pass in front of the corona, or that the corona itself may change in size. This variability underscores the dynamic nature of the region, emphasizing that even close to the black hole conditions are not static but in constant flux. The presence of the corona raises questions about how it is heated. Several mechanisms are proposed, with magnetic reconnection being a leading candidate. In this process, tangled magnetic field lines in the disk snap and reconnect, releasing enormous amounts of energy that heat electrons to extreme temperatures. This mechanism is analogous to solar flares in the Sun's atmosphere, though on vastly larger scales. In Markarian 231, the turbulent conditions of the accretion disk provide ample opportunity for magnetic reconnection, making it a plausible explanation for the corona's extreme heat. Other possible contributors include shocks in the inflowing gas and dissipation of turbulence at the disk's surface. The corona also plays a role in shaping the broad emission lines observed in the quasar's spectrum. X-rays from the corona irradiate the disk and surrounding gas, causing them to fluoresce in characteristic lines. For example, iron atoms in the disk emit X-rays when struck, producing features that are broadened by the disk's rotation and gravitational effects. In this system, such features provide some of the most direct probes of the innermost accretion flow. By analyzing them, astronomers can estimate parameters such as the black hole's spin and the inclination of the disk. Although heavy obscuration complicates these measurements in Markarian 231, the principle remains crucial for linking corona physics to black hole properties. Another significant function of the corona is its connection to the launching of winds and jets. While broad absorption line winds arise primarily from radiation pressure, The high-energy photons and magnetic fields associated with the corona contribute to driving gas upward from the disk. Some models propose that the base of relativistic jets originates in regions heated and magnetized by the corona. In this way, the corona is not merely a byproduct of accretion, but an active participant in feedback processes that extend across the galaxy. In the case of this system, the presence of large-scale outflows hints at such connections, though direct evidence of strong jets remains limited. From a broader perspective, the corona demonstrates how black hole accretion produces energy across the spectrum. While the disk dominates in optical and ultraviolet, the corona extends emission into X-rays, and the obscuring torus reprocesses it into infrared. Each component contributes a piece of the total energy budget. In Markarian 231, the unusual balance between these components highlights the diversity of quasar structures. Unlike some systems where X-rays dominate here, the infrared output is far stronger, showing that the corona's relative contribution can vary widely depending on the environment. Visually, the corona would not appear as a distinct object, but as a halo of light surrounding the inner disk invisible to human eyes, but blazing in X-rays detectable by telescopes. It would resemble a ghostly glow hovering above the disk, flickering as magnetic fields twist and reconnect. To an observer capable of seeing X-rays, it would appear as the most energetic region of the system short of the event horizon itself. Its light would pierce the surrounding dust, marking the nucleus as a source of extreme high-energy radiation. The corona represents another step inward on the journey through this galaxy. It is the zone where thermal radiation from the disk is transformed into X-rays, where magnetic fields release energy, and where variability is most apparent. For Markarian 231, the corona underscores the complexity of active nuclei, demonstrating that no single component defines the system, but that each plays an essential role in the overall behavior. The inward progression now approaches the very edge of the black hole's influence, where magnetic fields and angular momentum transport dominate, and where matter orbits in the last stable paths before plunging into the event horizon. Markarian 231, approached now at scales just beyond the event horizon, directs focus to the role of magnetic fields and the transport of angular momentum in the accretion process. Gas orbiting in the disk cannot fall directly into the black hole because its angular momentum keeps it in motion around the center. For accretion to proceed, this angular momentum must be transferred outward, allowing material to spiral inward. The mechanism that accomplishes this is primarily magnetic turbulence, where fields embedded in the ionized gas become stretched, twisted, and unstable. These instabilities, known as the magnetorotational instability, generate turbulence that redistributes momentum between neighboring regions of the disk. In effect, magnetic fields act as a kind of invisible viscosity, carrying angular momentum outward and allowing mass to sink closer to the black hole. Without this process, the disk would remain static with gas orbiting indefinitely. The environment of this galaxy is especially suited to strong magnetic interactions. The abundant gas supply from the merger provides a dense and ionized medium ideal for coupling with magnetic fields. As the disk rotates at speeds approaching a significant fraction of the speed of light, field lines wind up creating stresses that act on the plasma. This winding amplifies the fields, making them stronger and more effective at transporting momentum. In Markarian 231, the efficiency of this process is reflected in the high luminosity of the quasar, for it is only through efficient angular momentum transfer that so much gas can accrete and release energy. The interplay of fields and turbulence also generates heating. As magnetic energy dissipates, it warms the plasma, contributing to the temperature profile of the disk. This heating, combined with radiation pressure, influences the vertical structure of the disk, causing it to puff up in the inner regions. Models suggest that in luminous systems like this, magnetic support may even dominate over gas pressure, altering the shape of the accretion flow. In such regimes, the disk becomes more unstable, prone to fluctuations that may explain observed variability. For astronomers, detecting signatures of magnetic turbulence is indirect inferred from the behavior of the disk and from polarization measurements. Yet these signs point consistently toward a central role for fields in shaping the accretion process. Angular momentum transport is not uniform. Some regions of the disk lose momentum more rapidly than others, producing variations in accretion rate. These variations propagate inward, causing flickers in the brightness of the nucleus on timescales from days to years. In Markarian 231, such variability is observed across multiple wavelengths, evidence that instabilities in the disk influence the entire energy output. The connection between turbulence, momentum transport, and variability emphasizes how deeply magnetic processes permeate the nucleus. Even light that travels millions of light-years to reach Earth carries imprints of fields that operate within fractions of a parsec from the black hole. The importance of magnetic fields extends beyond the disk itself. They channel gas into outflows and may provide the seed for relativistic jets. Although this system is not dominated by bright extended radio jets, like some quasars, evidence suggests that magnetic processes still accelerate winds and shape their geometry. Broad absorption line outflows and disk-driven winds may arise partly from magnetic launching, where field lines anchored in the disk fling gas outward along rotating paths. This magnetocentrifugal acceleration is another way in which angular momentum is transferred with gas carrying it outward as it escapes. Thus, the same fields that allow accretion also drive feedback, linking inflow and outflow at the most fundamental level. The magnetic nature of the inner regions also has implications for the spin of the black hole. As gas carrying angular momentum accretes, it transfers not only mass but also spin to the central object. Over cosmic timescales, this process can alter the rotation rate of the black hole, influencing how efficiently it extracts energy from infalling matter. In Markarian 231, the sustained inflow from the merger suggests that the black hole has grown rapidly and may possess a high spin, though measurements remain uncertain due to obscuration. If the spin is indeed high, magnetic interactions at the innermost orbits may become even more significant, potentially powering relativistic effects that influence the entire system. Theoretical models of accretion emphasize that magnetic turbulence is unavoidable in ionized disks. The magneto-rotational instability arises whenever there is differential rotation, and in an accretion disk, inner regions orbit faster than outer ones. This shear naturally couples with weak magnetic fields to produce turbulence. The turbulence grows, redistributes momentum, and maintains the accretion process. In the luminous environment of this galaxy, such turbulence is likely extreme, with fields amplified to high strengths and energy dissipation occurring constantly. The result is a disk that is both luminous and unstable dynamic on timescales observable from Earth. Observational evidence for magnetic activity comes in several forms. Polarization of light caused by scattering in magnetized plasma offers one clue. Variability in emission lines reflecting turbulence in the disk offers another. X-ray timing studies reveal rapid fluctuations consistent with magnetic reconnection events. In Markarian 231, these clues combine to suggest a nucleus dominated by magnetic processes, even if the fields themselves cannot be directly imaged. They shape not only the accretion flow, but also the radiation that emerges from it. If one could visualize this magnetic environment, It would appear as a constantly shifting web of invisible lines threading through the disk, twisted tighter with each orbit breaking and reconnecting in flashes of energy. Gas clouds would be tugged and accelerated along these lines, spiraling inward as they lose momentum. The light emerging from the system would flicker as the turbulence rose and fell, carrying the imprint of processes too small to see directly, but too powerful to ignore. The corona above the disk would glow with energy, released by reconnection, while outflows would trace paths along open field lines extending outward. For galaxy evolution, the significance of these processes cannot be overstated. Magnetic turbulence ensures that black holes can grow by accreting matter efficiently. At the same time, the same fields launch winds and perhaps jets that regulate star formation across the host. Markarian 231 provides a vivid example of how these dual roles operate in practice, sustaining both the brilliance of the quasar and the feedback that sculpts its galaxy. The magnetic heart of the system links scales from the event horizon to kiloparsecs, a chain of influence stretching across many orders of magnitude. The inward journey has now reached the threshold of the innermost stable orbits, where gravity, radiation, and magnetism converge at their most extreme. Here, angular momentum has been stripped away, and matter plunges into the final spiral before crossing the point of no return. It is at this stage that the influence of magnetic fields becomes inseparable from the geometry of space-time itself, guiding the last motions of gas as it nears the event horizon. Markarian 231, followed still further inward, now reaches the domain of the innermost stable circular orbits, where matter approaches the very brink of the black hole. At this scale, gravity dominates every other force, curving space-time so strongly that the paths of gas and photons bend tightly around the center. For a non-rotating black hole, the innermost stable orbit lies at 3 times the radius of the event horizon. But if the black hole spins rapidly, as many models suggest for this system, the orbit can be even closer, shrinking to only 1.5 times the horizon radius. The precise location depends on the black hole's spin, and while direct measurements are challenging in this heavily obscured quasar, the immense luminosity implies a fast-spinning object capable of drawing gas into extremely tight spirals. At these distances, matter whirls around the black hole at significant fractions of the speed of light. Orbital periods shrink to hours or even minutes, and the gas is heated to temperatures of millions of degrees. Radiation emerges primarily in X-rays, with emission lines broadened and skewed by both Doppler effects and gravitational redshift. Observations of such features, especially from iron atoms fluorescing under X-ray illumination, provide one of the few windows into the conditions near the event horizon. In Markarian 231, heavy obscuration complicates the direct detection of these lines, but hints of them suggest that the gas orbits close to the black hole at extraordinary speeds. The physics here differs fundamentally from that of outer regions. Gas is no longer free to orbit at any distance, but is confined to a narrow range of stable paths. Inside the innermost stable orbit, matter plunges inward, with no further resistance, crossing the event horizon and vanishing from view. The boundary between stable orbits and the plunging region marks a profound transition. Energy release is at its peak just outside this boundary, making these orbits the most luminous part of the accretion disk. The efficiency of energy conversion depends strongly on spin. A rapidly rotating black hole allows matter to orbit closer, extracting more energy before crossing the horizon. If this galaxy's black hole does indeed spin rapidly, the efficiency of its accretion may be among the highest possible. Time dilation near the innermost orbits means that processes appear slower to distant observers. Photons climbing out of the deep gravitational well lose energy emerging redshifted. This effect broadens spectral lines and skews them toward lower energies, producing the asymmetric profiles observed in many quasars. In Markarian 231, even partial detection of such features carries significance, for it confirms that the gas extends deep into the relativistic regime. The combination of Doppler shifts from orbital motion and gravitational redshifts from spacetime curvature imprints the signature of Einstein's general relativity onto the spectrum. Variability in emission also reflects the dynamics of these innermost orbits. As clumps of gas orbit the black hole, their emission fluctuates on timescales of hours to days. Astronomers monitoring the light curves of quasars detect quasi-periodic oscillations that may correspond to orbital frequencies at these scales. While such signals are difficult to isolate in a heavily shrouded galaxy like this one, their presence in other systems strengthens the case that rapid variability can trace the motion of matter near the innermost orbits. For this quasar, long-term monitoring suggests irregular flickering consistent with instabilities near the boundary of stability. The innermost stable orbits also represent the region where magnetic fields become intertwined with gravity itself. Field lines anchored in the disk are dragged by the orbital motion of plasma winding tighter as the gas approaches the horizon. These twisted fields may extract rotational energy from the black hole through processes such as the Blandford-Zanayak mechanism, converting spin into electromagnetic power. In some quasars, this power emerges as collimated relativistic jets. In Markarian 231, large-scale jets are not dominant, but the presence of strong winds hints that magnetic extraction of energy plays at least some role in driving feedback. The interplay of fields and gravity at these radii is one of the most extreme examples of physics known. From a theoretical standpoint, the study of innermost orbits is crucial for testing relativity. The shape of emission lines the timing of variability, and the efficiency of accretion all depend on the geometry of spacetime near the black hole. In this luminous quasar, the inner disk provides a laboratory for these tests, even though dust and absorption limit what can be observed. Every photon that escapes from these radii carries with it the mark of curved spacetime encoded in its energy and trajectory. The challenge for astronomers is to separate these signals from the obscuring material farther out, but progress continues with high-resolution X-ray spectroscopy and long-term variability studies. The innermost stable orbits also define the point of no return for gas. Outside material may still radiate and contribute to the quasar's brightness. Inside, it plunges irreversibly into the horizon, its energy largely lost to the outside universe. This transition shapes the overall efficiency of the quasar and determines how much of the accreted mass is converted into light. In Markarian 231, the high luminosity relative to estimated accretion rate suggests a black hole that extracts energy efficiently consistent with rapid spin and a small innermost orbit. Such inferences link galactic scale observations to the physics of black hole rotation. Visually, if the obscuring dust was stripped away, the innermost disk would appear as a brilliant ring of light surrounding a dark center. The light would be distorted with the side moving toward the observer, appearing brighter due to Doppler boosting, and the opposite side appearing dimmer. The ring would seem skewed, its shape bent by the warping of spacetime. Just inside, darkness would dominate, marking the region where orbits end and the plunge begins. To human eyes, it would resemble the iconic silhouette of a black hole, though in reality it would flicker with the motion of gas clumps and flare with magnetic reconnection events. The inward journey has now reached the threshold of the black hole itself. The gas here orbits at breakneck speeds, radiating its last energy before disappearing forever. It is the innermost zone where physical laws are pushed to their limits, where relativity governs every motion, and where the transition from luminous accretion to silent absorption takes place. For Markarian 231, these innermost stable orbits define the edge of its brilliance, the boundary where energy is released most intensely before matter is swallowed. The next step will lead into the regions where jets may be launched, where magnetic fields and relativistic plasma escape, even as most matter falls inward. Markarian 231, examined at the edge of the black hole's domain, now presents the zone where jets may be launched, regions where magnetic fields and plasma interact to produce narrow beams of energy, capable of stretching thousands of light-years into space. In some active galaxies, these jets dominate the outward appearance, forming bright radio lobes that extend far beyond their hosts. In this system, however, large-scale jets are not prominent yet. Evidence of compact emerging structures and faint radio signatures suggests that jet launching still occurs near the event horizon. Even when not visible as spectacular radio outflows, the underlying processes remain essential, linking the magnetic fields of the accretion disk to the broader mechanisms of feedback. The theory behind jet launching begins with the twisting of magnetic fields in the innermost disk. As plasma orbits close to the black hole, field lines are wound tighter and tighter, storing energy like stretched elastic bands. If the black hole spins rapidly, the dragging of space-time itself winds these fields even more strongly. Under the right conditions, the tension in the fields accelerates plasma outward, along narrow channels forming jets that escape perpendicular to the disk. This mechanism, known as the Blandford-Znajek process, extracts rotational energy from the black hole itself, converting spin into electromagnetic power. Another related mechanism, the Blandford-Payne process, flings material outward, centrifugally along open field lines anchored in the disk. Both processes rely on the extreme magnetic environment of the inner orbits, where gravity and fields interact at their highest intensity. Observationally, Markarian 231 shows evidence for compact radio emission near its nucleus, consistent with the base of a jet. Very long baseline interferometry reveals small-scale structures extending outward, though they dissipate within hundreds of parsecs, rather than continuing into vast lobes. This suggests that while jet launching occurs, the dense environment of the galaxy disrupts their growth, confining them close to the core. The presence of strong winds and abundant interstellar matter may choke off larger jets, leaving only compact outflows detectable in radio. Even so, these outflows demonstrate that magnetic extraction of energy is active, and that the black hole's spin contributes directly to feedback. The properties of these jets, though modest compared with those in giant radio galaxies, still affect the immediate environment. Compact jets inject energy into the circumnuclear medium heating gas and contributing to turbulence. They may also accelerate cosmic rays, high-energy particles that permeate the galaxy. In Markarian 231, such contributions are difficult to separate from the effects of radiation-driven winds, but the coexistence of both emphasizes the multiplicity of feedback channels at work. Jets may be weaker here, but they add to the overall picture of a nucleus influencing its host in every possible way. The relationship between jet launching and variability is another area of study. In some quasars, bursts of activity in the accretion disk lead to flares in the jets, visible as sudden brightening at radio or X-ray wavelengths. Monitoring of this system reveals occasional flares that could correspond to such events, though heavy obscuration complicates interpretation. If present, they suggest that the same instabilities driving changes in the disk and corona also modulate the launching of plasma along magnetic fields. This coupling further highlights the tight connection between processes occurring at the event horizon and those affecting the galaxy on much larger scales. Theoretical models of jet launching emphasize the importance of spin. A rapidly rotating black hole can contribute significant energy to jets, while a slowly rotating one produces weaker outflows. For this galaxy, the high luminosity and efficiency of the accretions suggest a fast spin, making it plausible that energy extraction through jets is ongoing. Even if large-scale jets are absent, the spin still influences the dynamics of the nucleus, shaping how energy is partitioned between radiation winds and compact plasma flows. Visually, if the obscuration could be stripped away, the jet-launching region would appear as a bright, compact core with thin beams of plasma emerging perpendicular to the disk. These beams would be narrow but intense, glowing in radio and X-ray light, as particles accelerated within them radiated synchrotron emission. In Markarian 231, the beams might fade quickly into the surrounding medium, absorbed or dispersed by the dense gas. To an observer, they would appear like sparks from a fire, brief but powerful, carrying away energy from the deepest gravitational well. The significance of jet launching, even in modest form, is that it demonstrates another path for black holes to influence their galaxies. Radiation heats gas winds, push it outward, and jets inject energy into narrow but deep channels. Together, these processes ensure that no galaxy with an active nucleus can evolve in isolation from its central engine. In this luminous quasar, the combination of broad absorption line winds, kiloparsec outflows, and compact jets illustrates the full spectrum of feedback. Each mechanism contributes differently, but all originate in the physics of the innermost orbits. For astronomers studying the jet-launching zone in nearby systems like this one, provides essential data for understanding more distant quasars where jets dominate. It shows how even a system without giant radiolobes still employs magnetic extraction of energy. The presence of compact jets in such an obscured infrared bright galaxy underscores that jet formation is a nearly universal feature of black holes, though its expression depends on the environment. Markarian 231 thus serves as a bridge between radio-quiet and radio-loud quasars, revealing how the same fundamental processes can appear differently under varying conditions. The inward journey has now reached the transition between the disk and the larger universe, where magnetic fields twist plasma into beams and hurl it outward. These jets, though not dominant in this system, mark the final stage of direct energy release before attention turns to how the light itself varies, how delays across wavelengths record the finite speed of photons, and how the inner processes reveal themselves through their timing as much as through their power. Markarian 231, traced to its innermost workings, now reveals its nature through multi-wavelength variability and the delays that come from light's finite travel time. Unlike the large-scale structures of tidal tails or starburst rings, these variations occur on timescales of hours, days, and years, providing direct evidence of processes happening close to the event horizon. When astronomers monitor the galaxy across the electromagnetic spectrum from radio to X-rays, they find that its brightness flickers irregularly, sometimes dimming, sometimes flaring, and often shifting differently at different wavelengths. These fluctuations are not random noise, but the natural outcome of turbulent accretion, unstable winds, and the interplay of disk corona and obscuring material. In this system, variability is particularly complex because obscuration and reprocessing add layers of delay, but the signals still carry the imprint of the black hole's environment. At the heart of variability is the structure of the accretion disk. Gas does not flow inward at a steady uniform rate, but in clumps and streams. As these irregularities reach different radii, they cause temporary changes in brightness. When a surge of gas moves inward, the luminosity of the disk increases, producing a flare that may first appear in ultraviolet light, and then later in optical, as the radiation is reprocessed by outer zones. Such delays between bands are known as reverberation lags, and they provide one of the best tools for mapping the disk. In Markarian 231, reverberation mapping has been attempted, though heavy dust complicates observations. Still, hints of time lag suggest that inner fluctuations echo outward, carrying information about distances and geometry that cannot be seen directly. The corona adds another layer of variability. Changes in its size or temperature alter the strength of the X-rays, which in turn irradiate the disk and cause secondary responses. When the corona brightens, the disk reprocesses more energy, leading to correlated but delayed changes in optical and infrared light. This chain of cause and effect produces a complex pattern of variability, with some wavelengths leading and others lagging. In this galaxy, the X-ray variability is unusual, sometimes weaker than expected, sometimes heavily absorbed. Yet even in its peculiarity, the system provides valuable data showing how obscuration and geometry shape the timing of signals. Dust in the torus also participates. Radiation from the inner regions heats the dust, which then re-emits in the infrared. Because the dust lies at distances of hundreds of light years, its response to changes in the nucleus is delayed by months or even years. Thus, long-term monitoring reveals echoes in the infrared that trace the history of nuclear activity. In Markarian 231, the infrared output is dominant, making it an excellent subject for such studies. Variations observed years after X-ray or ultraviolet changes confirm that dust reprocessing is a major channel of energy release. These echoes extend the timeline of variability, linking short-term flickers to long-term trends. Another important aspect of variability is its link to outflows. Winds launched from the disk can alter the observed light by adding absorption features that change with time. As clouds move across the line of sight, they block portions of the spectrum, deepening or shallowing absorption troughs. Such changes occur on timescales of weeks to months, depending on the speed and distance of the clouds. In this system, broad absorption line features vary significantly, confirming that the winds are clumpy and dynamic. These variations are not mere details, but essential clues to the structure and motion of the outflows, showing that they are neither smooth nor steady, but composed of countless shifting elements. Variability also reflects the finite speed of light itself. Because photons take time to travel across the different regions of the nucleus, changes propagate outward with measurable delays. This principle allows astronomers to use timing to measure size. For example, if X-ray changes are followed days later by optical changes, the distance between corona and disk can be inferred. In Markarian 231, where direct imaging of the nucleus is impossible, such timing methods are among the only ways to measure scales of light days to light weeks. The data, though noisy, indicate that the nucleus is compact, consistent with theoretical expectations for a supermassive black hole. On longer timescales, variability provides evidence of the galaxy's evolutionary stage. Over decades of observation, the system has shown changes in brightness that suggest transitions between different modes of accretion. Periods of relative calm alternate with periods of intense activity, perhaps reflecting the inflow of large clumps of gas or the clearing of obscuring clouds. These cycles may represent the natural progression of a merger-driven quasar, where the supply of gas is irregular and the feedback is disruptive. In this sense, variability is not only a probe of inner physics, but also a reflection of the galaxy's history and environment. From a theoretical perspective, variability is expected in any turbulent magnetized accretion flow. Magnetic reconnection, shocks, and instabilities all produce fluctuations. In luminous systems, radiation pressure adds further instabilities, making the disk prone to sudden changes in thickness and output. Markarian 231 exemplifies these processes. Its irregular light curves confirm that accretion is not smooth, but episodic, punctuated by bursts and dips. For astronomers, these light curves provide laboratories for testing models of turbulence radiation transport and magnetohydrodynamics under extreme conditions. Visually, variability would appear as flickers and pulses in the brilliance of the nucleus, like a lantern whose flame shifts with every gust of wind. To human eyes, the changes might be imperceptible over hours, but obvious over months as the quasar brightens and fades in cycles. To instruments sensitive across wavelengths, the variability is rich with detail, each flicker revealing a new aspect of the structure. Infrared echoes would appear as afterglows, while X-rays would flare like sparks above the disk. Together they would create a complex but coherent pattern, a dynamic portrait of a black hole's feeding. The importance of multi-wavelength variability lies in its ability to connect regions that cannot otherwise be observed. Timing bridges scales, linking corona to disk-disk to torus and torus to starburst regions. In Markarian 231, these connections are clearer than in most quasars because of its proximity, even though heavy dust makes observations difficult. By comparing changes across bands, astronomers reconstruct the geometry of the nucleus piece by piece, like mapping an unseen landscape through echoes. The results confirm that the galaxy is not static, but alive with motion, every part responding to changes in the others. The inward journey concludes with this recognition: the smallest scales of the nucleus, where radiation and particles interact near the event horizon, reveal themselves not through static images, but through variability and timing. These signals, measured across light years and over decades, show how intimately the galaxy is bound to its black hole. In Markarian 231, the flickers, echoes, and delays are not distractions, but the clearest messages from its hidden heart. They demonstrate that the quasar's power is not constant, but dynamic, shifting with the rhythms of turbulence and the limits of light speed. With this final step inward, the exploration has reached the smallest observable workings of one of the universe's nearest and brightest quasars, completing the passage from outer halo to innermost light.